called on the cloud. So let's start now with this fourth lesson. Today we will concentrate on again on some basics about Dynamo. Just a few things about lists and what is called lacing. Then we will move to solids elements, and finally we will try to import something directly into the Revit viewport. So today we are going to start to build something directly from Dynamo into Revit. So I'm going to open Dynamo. Don't worry about what is here in the viewport. We will see this later. So let's start a new file. So what I want to introduce you now, now we have a big introduction about Dynamo, but we didn't focus actually on how Dynamo is managing elements, lists, and other things inside. So I just want to do a little step back, just to introduce you what is the meaning of lacing in nodes. So to try to explain this to you, I'm just going to draw a bunch of points. So from 0 to 10, and from 0 to 5. And let me pick the point by coordinates. This is 10, and then Control C, Control V. This is 5 points. I just want to move a little bit up all this list of points. And then I can zoom to fit. So we have two lists of elements. And let's say we want to connect these points together with a line. So we can use the line by start point, end point, and we can connect these points. So according to these two lists, we have a different number of elements actually, because we have 10 elements, actually 11 elements in this first list, and we have 6 elements in this second list. So when the line by start point, end point is going to connect these two elements, these two different lists, he's trying to connect the first point with the first point, and the second point with the second point, and so on. So once the first list is finished, the list by start point is not going to connect any other line, because we don't have any other point to connect the two lines. And this is because we have a lacing set into shortest. So the lacing is this small thick here in the bottom right of the node. And if I right click on top of the node, I can see we have a lacing option, and we have 3 options. So the default option is shortest. That means that the node will try to connect 2 elements using the shortest amount of elements in the 2 lists, 2 or whatever list we have. If we're going to change the lacing into longest, so then the node will try to connect all the elements of the longest list with the other list. And because we don't have any kind of point able to connect these remaining points, the node will try just to connect with the latest one available from the second list, and will connect this point with this element. We have another option, and then we have which is called cross product, and the cross product will just try to connect each single point with each single point of both lists. So the first point with all the points from the second list, the second point with all the points to the second list, and so on. So then the cross product will just appear something like this. So it can be useful sometimes if you need, especially if you need to find some intersection between different elements and you want to find all the intersections between two lists of geometries, then the cross product is the right choice. But if you just need to connect elements, sometimes you use the shortest one and sometimes you just use the longest one. It depends on how you want to connect elements between each others. So this is a very important point in Dynamo, and we will use this many times, and sometimes the result of your workflow can change dramatically if you change the type of lacing. So be careful, because sometimes you will need to change it from shortest into longest. Let's say that probably 70% of the times you will use the shortest connection because you have more or less always the same amount of information that you want to connect. Sometimes you need probably 20% of the times you will need the longest one to be used. And let's say just 10% or 5% of the times you will need the cross product. So it's very unlikely used, but sometimes you need to use it. I have another, we can say that, for example, we have two numbers. So let's make another example. We have 2 and we have 3, and then we have a list. So to create a list, if you remember, we use the list create. And this is going to build a list of elements. We have another way to create a list in an easiest way, which is always using the code block. We open the brackets, and inside we are going to write the numbers or whatever we want, split it by comma. So this is the same exact way to write a list using the code blocks. It's easy to write it in this way. You can write also a string using this syntax. For example, is a list of string or is a list of name, for example. And you can even nest lists. If you open another one and you do the comma here, and for example, you copy and paste another list here. So we have two lists. You can also write in this way, which is the easiest way to do it. So remember, you have to split the list elements between using a comma, and you can also use nested list. So if I'm going to do this one, you have two lists, one with name, surname, and the other one with name, surname again. Let's say name 1, surname 1, and so on. So instead of doing this representation, you can do also this one, which is a little bit more easy to understand, even for someone which is not very, which is not using Dynamo. So let's say we have a list of numbers, and I'm going to write it down in the right way. 1, 2, 3, 1, 2, 5, and this is 2 and 3. And we have another list of numbers, and we have 1, 2, 3, 1, 2, 5, and let's say 5, 4, and 6. So if I try to multiply these numbers between them, what I will have is that I will have 2 multiplied by 5, which is 10, and 3 multiplied by 4, which is 12. If I change this one into a longest, then I still have 6 multiplied by 3, because it's the longest list which is driving the node. But if I want all of them multiplied by all each other, I can go and do a cross product. So I have the first list multiplied by the second list. So 2 by 5, which is 10, 2 by 4, which is 8, 2 by 6, which is 12, and then again 3 by 5, 3 by 4, and 3 by 6. So those are just two different examples to understand how can work the lacing in different kind of lists. Sometimes you have geometries, sometimes you have numbers, sometimes you have strings, but it works always in the same way. Shortest is driven by the shortest list, longest is driven by the longest list, and cross product is the first one multiplied by all the elements of the second one. So with this in mind, let's say I will save this in a group saying this is a lacing example. Remember, to create a group, you just select elements and you press Ctrl G, or you go under the edit menu under create group, which is Ctrl G, and then you can double click to change the description, or you can right click to change colors or font size, or if you want to ungroup or delete the group, you can do it from here. So let's save this one right now, which is the lacing. The other one, let's say 0, 0. The other information that I want you to know before starting the next step is how we can flatten a list. So sometimes, especially if you have lists done in this way, so you have nested list of elements, sometimes you just want to remove these sublists and keep only one list, one single list with all the elements together. So this is called flatten list. And there is a node called flatten, and connecting this list to a flatten node, the result will be exactly the same list of elements, but this time without any kind of nesting. For example, we want to create this list, and then we want to sort the list. So if we sort the list using the first one, what I will receive is a sorting of the sublists inside. But if I want to sort all the elements together, then I need to sort the flattened list. So this is working in a different way if you connect the flattened version of this list, or if you connect this node to the original list. So be careful when you use Dynamo, because every time you have to check if you want to do something between a flattened list or you want to do something inside the nested list. So this is really important. You will get used to understand when you need to flatten a list, and I will show you later an example about this one. So let's say this is flatten node. We have someone in the chat. Can we sort the list by other criteria like longest to shortest? Of course, yes. We have other kind of sort, like sort by value, or we have sort by function. So we can find a function to sort. We can sort by key, for example. So I will show you, if you have a list of elements, so let's say we have like names, name 1, name 2, and name 3. And then we have another list. And this time we have a list with 3, 2, 1. We can sort this list of names based on this list of keys. So let's say we want this list and we have this the keys at the same time we sorted the first list based on these keys, which is exactly the opposite one. So instead of using names and numbers, you can use any kind of other things. So we can sort, for example, these lines in the first list as a list, and we can give key as a key the length of these curves. So I will show you this example very quickly. We have a node which is called curve length, and we can connect this curve length to these lines. So let's say we want to connect this one. Let's remove these connections. So we have these lines and we have the length of these lines. Of course, the first one will be, the first 6 lines will be with the same length. So if we want to sort these lines, we can connect the lines to the first one and we can connect the length with the keys. So right now, of course, we have the same connections, I mean, the same order, just because we know that these lines are gradually longer than each other. So we know that this one is longer than this is longer than this one, and so on. But if we have multiple lines and we just want to connect them and we want to order them based on the on their length, we can do something like this. So you can order whatever you need. You can order list of strings, you can order list of curves or solids based on their volume or whatever you want. But this is working in a different way if you use the normal list, if you have a nested list, or if you use the flatten list. So sometimes you need to use the flatten node. Is this okay? Is this clear? I think perfect. So with these two informations, we can start to build something a little bit more complicated compared to what we did until today. So to do that, we need to introduce some basic concept about geometry in Dynamo. So I don't want to bother you with geometry, with a college geometry lesson, but I can say that it's really important to understand the basics of planar geometry and 3D dimensional geometry, because most of the times you will deal with curves, with planes, with normal vectors or tangent vectors or angles and so on. So it's really important that you learn some basic stuffs, but it's really important that you learn these elements. So let's say we want to continue on this side, and we can just say that we don't need any more of this, so we can remove the preview of these elements and these points. Let's hide all the geometries. So what is a plane dynamo? The plane, or what is a plane in the geometry, is just an unlimited place of points in the 3D space, which can be created in different ways. But every time you have a plane, you have a normal. What is a normal? A normal is a vector which is exactly perpendicular to a plane. So a plane can be always created using an origin and a normal. The origin is the point where this normal is applied. So let's say this plane, default plane, has the origin in the 0, 0, 0, so in the origin of the axis, and the normal of this plane is the vector which is pointing to the z direction, so up. As I said in the first lesson, we have the z direction pointing up, the x direction pointing on the right side with the positive direction, and on the left side as a negative direction. And we have the y axis pointing in this direction as a positive, and in the opposite direction as a negative. So if you remember always this information, the red one is the x-axis, the green one is the y-axis, and the blue one is the z-axis. So according to this information, we can always create a vector using three components: the x component, the y component, and the z component. So if we want to create a different plane, we can create a new one, creating a new vector. This time is not a point, is a vector, and we can give three different values using, for example, a slider. So we can copy 3 times this, and we can connect these 3 elements to this vector. And right now we have a 0, 0, 0 vector, which is actually not possible, because the 0, 0, 0 vector means that we have a point, actually, because we need at least a value of different from 0 for one of these to have a direction for a normal. If I'm going to connect this to the normal, we can see that the plane is not showing because we don't have actually a normal, we have a point. So we cannot create a plane if we don't have a normal. But as soon as I'm trying to move this element, you will see that no matter the value of the x, we have a vector pointing in the x direction. And this value is called magnitude of a vector. So it's the power of the vector, the length of the vector. And if I'm moving now this x value, you can see that the plane is just moving in the x, y plane, because this vector is pointing and is moving around the x, y plane. And as soon as I'm starting to move also the x direction, the z direction, you can see that this plane is pointing somewhere. And this vector is actually the normal vector of the plane. So this is really important because we can use planes to create and place geometries that we can later on use as a cross sections. And I'm going to start now an example of this. So this technique that I'm going to show you now, it's always used when you have a section that you want to loft around a path, or just you want to copy along a path. So let's say that this is the creation of a plane. So Control G, and this is plane creation. we can immediately start to use this plane, creating, for example, a circle, because we can create a circle in many ways, and one of these is by plane and radius. So the first one is created on an XY plane, but as soon as we connect this plane to the circle, we can see that the circle is exactly based on the plane now, because it's using its normal to orient in the 3D space. And then of course we can copy and paste here, and we can start to build our circle. And anyway, now you know that you can connect sliders to manage double information, numerical information in Dynamo. So keep in mind that we have the possibility to create a plane. And every time you create a plane like this, you can recreate the 3 axes used by this plane. And it's like, you know, when you use AutoCAD, you can move the UCS in AutoCAD and just move the possibility to view in a different direction your drawing. And in Revit, you can create reference planes, and then you can set that reference plane just to draw your section. It's the same idea. So every time you create a reference plane, you have a normal for that reference plane. And every time you create an element on that reference plane, you are just using a new coordinate system to create that one. So we can extract from a plane a coordinate system. A coordinate system by a plane is just the new position of these 3 axes. So now we have the X pointing exactly, laying exactly on top of the plane, and the same, the Y direction is laying exactly on the plane, and the Z direction is pointing to the normal direction of the plane. So whenever I'm moving this plane, I'm also changing his coordinate system. And this is pretty amazing that you can see it in real time inside Revit, inside Dynamo, because this can give you exactly the idea on how the 3D world is working inside Dynamo. So you have your basic, your world UCS, your world coordinate systems, which is the one that I showed you at the beginning. And then you have local coordinates systems whenever you create a plane, and you can extract that coordinate system for the plane. So why I'm trying to show you all this information? Because the next exercise will be to create a simple shape which is laying down on the XY, and then this shape will follow a very complex path in the 3D world, rotating and then moving and then translating according to a spline that I'm going to build now. So keep in mind, a plane is always created with a vector normal, and the vector is created using 3 components that defines the magnitudes of the vector. And then based on a new plane, we can extract a coordinate system, a local coordinate system. So let's save this one, and we can open now this first exercise. I already prepared this one, but I will show you from the beginning how to build this, this node. So don't worry. So first of all, I used a little bit of code block like we did in the first lessons. So this one is exactly the creation of a range of numbers going from 0 to 360. And then I have also a multiplier because this is a torching elements. You will see now it's quite complicated in the 3D space. So I'm just saying I want to go from 0 to 360, or for example from 0 to 360 multiplied by 3, or from 0 to 360 multiplied by x. And I want a step increment between 0 and the final number of 5 units. Be careful now, because now we are starting to build a geometry that we want to use later on in Revit. So the numbers that you are using here are related to the project units that you set in the Revit project or family. So I have used now meters here, and that's why I'm using these big numbers, because I'm actually building something that is huge. So I'm going from 0 to 360 meters, and I want a step of 5 meters. Be careful, because if you are using millimeters, 360 millimeter is a very small number. And if you try to build something very complex, probably Revit won't be able to create this element. So always be careful about numbers you are using here, especially if you are trying to create something inside Revit. So the Y element will be the same function that we used in the first or second lesson. It's an amplitude multiplied by the cosine of the x value plus a phase value. And for the z value, I'm using the same function, but this time with the sin value. The result of this is actually, let me show this, and let me, for now, I just want to disconnect this one. So let me go in run, and the result of this is a very nice shape, a very nice curve. And as you can see, I can change, let me open a little bit more probably. Let me go here, zoom to fit. So if I'm going to change this value, is changing the y direction, because it's changing the amplitude in the y direction and both in the z direction. And this is the phase, so I can using this one like a screwdriver, and I can multiply. So I can, with this multiplication, I can build more, let's say, like springs element. So I can go a little bit more or a little bit less here. So it's pretty simple. Those are the 3 points. And you can see that between each other, we have an increment of 5 units. We can see it if I'm going to make it a little bit far from each other, or we can build again with an increment of 5. So it's pretty simple, and it's just what we did in the first lesson. And then I have a curve based on these points. And this curve is a NURBS curve, and the degree of this curve is 3. So it's pretty simple to build this one. So the next one, it's a very, very important node. It's called curve.plane@parameter. Remember the concept of parameter of a curve, as I explained in the probably the previous lesson, I said that every kind of curve has always a parameter going, a value of the parameter going from 0 to 1, cannot change this value. What we can change is the number of subdivisions. So this amazing node is able to create a perpendicular plane to a curve based on the value of a parameter. So using this, I'm just creating a range going from 0 to 1 with 50 subdivision. Remember the hash character here. So we have 50 subdivisions going from 0 to 1. And then we can create, let me freeze this one now. And then we can create a plane which is always perpendicular to the curve. And this is really nice because the curve is really complex. And can you imagine how you can place this plane around the curve, and with this curve changing direction almost every time in his during his length? So then I just use the simple circle by plane, and again you can stop the execution of a workflow freezing a node instead of removing the preview of the node. So I can build again and freeze from here to here. Freezing is locking the next nodes connected to the one you are freezing. So it's very good if you want to go step by step. So now I just have these nice circles based on our curve. And what I'm using now, it's just for fun. I'm creating a geometry scale node, which is taking as an input the geometry that you want to scale, the plane you are using to scale the geometry. So these planes are really important. And the final result is actually how I want to scale this, the amount of scaling along the x-axis, the y-axis, and the z-axis, which is the local coordinate system based on this plane to scale these elements. So I can preview this one and just remove the preview of this one. And I'm saying I want to go from a scale factor of 0.1 to a scale factor of 5, and I want the same number of subdivisions that we are using to create the planes. So we have exactly the same amount of scaling factor according to the same amounts of planes. So every time we have a plane, we have a different scale factor. So I can run this one, and as you can see, is growing from a number to the other. And last but not least, I'm creating the solid using the cross sections. So it's exactly what we saw in the previous lesson, but in the previous lesson, we used the surface by cross sections. This time, I'm using the same nodes, but I'm creating a solid cross section, which is this one. So we have both nodes similar for surfaces and for solids. The difference is pretty simple. If you use the surface by cross section, you just have a simple element without any solid. So it's just empty inside. It's just like a pipe. And if you create a solid cross-section, you have the solid one. So just run. And pretty nice. So this is completely parametric. I can go to automatic and I can, for example, change the scale factor. Let's say I want to go from 1 to 5. And then whenever I click outside, you can see that now it's changing the scaling factor. I can change the amount of times I want to build this one. So it's just like a cornucopia now. I can change whatever I need here. I can change the value, but the idea behind is that, again, you are starting from simple elements like points, and then you build curves, and then you build cross sections based on curves, and this time we are building cross sections based on planes, and based on that you can create surfaces or solids. So it's always the same idea. If you can break down the problem to simple problem, you can always find the right solution. So let's save this one now. This is the first example, because right now we are still inside Dynamo. So this node is not creating anything inside Revit. So it's just a Dynamo visualization. I'm prepared already another exercise similar in the first part, but a little bit different in the second part. So this part is exactly the same. But what I'm doing now is to use a different section, something that I drew in the workspace. So I just started with a new family, and remember, to do complex shapes, you can't use different template rather than the adaptive components. So you need to use either the adaptive components generic model or a mesh family, because they are the only one where you can model freeform elements. You can't model freeform in other kind of templates. So I'm always using this metric generative model adaptive as a starting point for a template. And of course, you can't model this freeform inside a project. You can't use these tools for freeform modeling directly in the project. So you have to use it in a family editor before importing these elements into a project. I will show you later in the course that you can do something directly in the project using other nodes. But let's say that as a rule, if you want to model some complex shape, you have to model it inside a family editor before using this element into a project. So it's pretty simple. It's just changed again the project units into meters. That's just for fun. Always, I like sometimes to enable the sketchy lines, especially if this geometry is something that is going to be like an architectural covering, or just something that is conceptual. I like to use this kind of lines. So the first thing I'm trying to do now again is to build this curve, and to do that, let me freeze this part, and let me freeze this part. So to do that, I'm again using the same exact component that we used in the other project. The next part is jumping on the bottom part of the system. I'm just extracting the section curves. So I drew this line in the canvas, and I can use a node called select model element if it is just only one element that you want to select, or I can select model elements if I need to select more than one. And because we have 8 lines here that we want to select, I'm using this select model elements. So it's the second one, not the first one. So if you click then on change, Dynamo is giving you the opportunity to select from the workspace something, and is providing you with the list of elements that you selected from the canvas. So let me freeze this one and go into run. As you can see, they are model curves. If I select one of these curves, is exactly a model curve, a line. And I already have these lines in my project here. So whenever I'm using this in automatic and I'm moving these lines, I have still a live connection between the two elements, live Dynamo and Revit. So, and this is pretty amazing when you are form finding something or you want to change the shape to see something in Dynamo. Then, because we can't use model curves in Dynamo, we need to convert these model curves into real curves. And we have a specific node to do this called element curves, which is exactly taking the curves from an element. And again, freezing this one, I have the list of curves. Remember when I said to you that sometimes you need to flatten a list before going to the next node? Because as you can see, at the first stage, we had a list of curves, but now we have a list of nested curves. And this is not good for us to go further in our definition, because we need to join these curves into a single curve. And to do that, before using the polycurve by joined curves node, which is exactly the node going to join these curves together into one curve, we need to flatten this list. So let's go up to here and run this one. I'm going just to remove the preview of this. And again, now we have again a curve here, but this time this curve is only one curve, is a polycurve. So it's a polygonal curve and is made by 8 curves, which are exactly the 8 curves that we used at the beginning, but it's a Dynamo curve now. It's not anymore a Revit curve. It's still binded to the Revit curve, but it's a Dynamo curve. So if I'm going to move again this one, it's still binded to, together. They are still binded together, but now we have a Dynamo curve. So whenever I have a curve, I can extract the plane where this curve is laying. And to do that, I can use this node called polycurve base plane. So it's just taking the direction, the normal direction, the average normal direction of this curve right now is laying on the XY plane and is creating a plane at the starting point of the curve, which is actually the beginning of the first curve we used to create the polycurve. Then I want to extract the coordinate system from this base plane, which is the same that we did in our first example today. So extract the coordinate, the local coordinate system for this element. And if I'm going to manual, this is exactly the coordinate system of this curve. We can move this coordinate system around, we can rotate this coordinate system, but basically now we know that this is the local system of this curve. So let's do the same with our planes. Remember, like in the first example, I've created a plane using the curve plane parameter, and then I have extracted the coordinate systems of these planes. So not less, not more. We have a coordinate system pointing in the right direction along the curve for each plane that we have on the curve. And we built a plane based on this number of subdivisions. So we can do more subdivisions, of course. So we have more planes and we have more coordinate system, or we can do less. The next node is the most important node in this workflow. And again, this is a node that you will use a lot, especially in this kind of works. So this is basically saying to use the geometry that we extracted at the beginning. So what is the section that we want to use as a base geometry? And then he's saying, use the coordinate system of this exact polycurve and just move this coordinate system to match these other coordinate systems. So is from to a context coordinate system. And this is acting really amazing because in just one click, we have our curves moving around the entire length of the curve, rotating in the same direction, staying always normal to the curve up to the end. And as you can see, it's something that it's more or less impossible to do in Revit with out-of-the-box tools. You can do it, but it's almost impossible to do it. So once we have these geometries, I just used again, you know, the scale elements. So let me disconnect this one. The scale element just to have something fancy. Again, like we did before, to make it from a very small piece to a very big section at the end. So it's pretty nice. It's useless, of course, but you can imagine that you can reach very important things in this way. So once we have this, again, we can create the solid in Dynamo. And this is just for you as a representation of the element inside Dynamo. Let me turn off the preview of each cross sections. I can turn off also the points or the NURBS. We don't need it anymore. We can just close some of these elements like the coordinate system. We don't need it. Let's remove this one and so on. So it's pretty nice. And again, it's almost impossible to do this rotation directly into Revit. But still, we don't have an element into Revit. To do that, we need to do two more operations. First of all, Revit doesn't like closed curve to create a section. In fact, as you can see, this element is like represented as an entire element, but as you can see, is made by different curves. So we need to do the same exact task. So we need to explode the element. And to do that, we have a geometry explode node. So we have now, again, not anymore a list of polycurves, but for each polycurve, we have 8 different curves with the starting point and the end point. And we have, again, 49 polycurves, and we have 49 nested lists of curves. So they are just exploded again. And the final one, before doing the real solid in Revit, it's to convert back into model curves the Dynamo curves. So remember, at the beginning, we used element curves to convert model curves into Dynamo curves. And right now, we need to do the opposite task. We need to convert Dynamo curves back into model curves. So we can do that. We can just run this. It's taking its time to draw these elements in the canvas. And in fact, we have the lines now back into Revit, and all of them are like reference line. Can you imagine to do this by your own? Impossible. And if you go back to Dynamo now, it's the time to use these curves to create what is called a form element. So it's pretty similar to the solid by loft, but this time is a form by loft. And this is making the difference between a Dynamo solid and the Revit solid. So it takes curves as an input, and we can run. And here we are. We have the final element inside Revit built on top of our geometry using our custom sections and using our custom function to lay down the elements in the canvas. So this is more or less the way I'm using to create curtain walls, substructures, complex substructures for shelters. You just need to draw the exact shapes that you want to replicate. You can do really steel structures, concrete structures in this way, very complex shapes, just using always the same way. Building a sections, building a grid of connected curves, and then use coordinate systems to place in the correct way the sections against the path, and then using the solid loft by cross sections to create the real solid inside Revit. And this is really used a lot in both architectural and structural. I use this one to build tunnels, to build any kind of structures that you want to build. And it's more or less what you need to know to build probably the 60 or 70% of shapes that you can build with Dynamo. So I'm going to save now this exercise for you to take it back later. Jose will send you together again the recording session of today together with the exercises. And I hope this was interesting for you because next time we are going to start to build something in a project like a small tower, and we will start to extract information using Dynamo to Excel or to any other kind of worksheets that we can use to build our dashboards or something related to the project. So the next part of the course will be focused on Dynamo to manage data and to manage projects, repetitive tasks, for example. So I suggest you to try to build a kind of shape And if you have any comments, or if you want to send me the file just to take a look into, just write me an email. I will try to reply to you as soon as possible. So let me go to the chat. And I hope you enjoy it again, and see you next week.